First, we have some housekeeping rules. This session will be recorded and shared, and feel free to ask questions in the comments. They will be answered at the end, and we will follow up on any questions not answered during the webinar. Over to you, Christian.
Well, good morning, everybody. Warm welcome from my side as well. I would like to introduce the participants on our side this morning. We have Christina, who's really the organizer and the heart of the entire organization of the webinar. She's our marketing expert. I'm the CSO at Radar Monitor. We have Niels. He's the COO and CTO, and Morten, whom you just heard, he's our area sales manager. And we also have, as you might have noticed on the first slide, we have a guest speaker today, who is René. He's a project manager with Geo. We prepared a small agenda for you today. First point, why slope and embankment monitoring matters. Then we have René, our guest speaker, who will tell you or share some of his expertise with you. We have some talks about slope and embankment monitoring strategy, real-world insights, and then to round everything off, we have a Q&A session for you. And please feel free throughout the session today to write your questions down. Thank you very much.
So thank you, Christian. And yeah, I will guide you through the webinar. And I said, my name is Niels. Well, we find ourselves in what we can describe as a perfect storm. Our railways are built on traditional methods that have served us well in the past, but today they face unprecedented challenges. Increased train speed and heavier loads place the additional stress on our infrastructure. Coupled with rapidly changing climate, bringing more intense and frequency rainfall, these factors create a volatile environment. We have unfortunately witnessed tragic incidents, such as fatal derailments caused by landslides and water erosion, which washed away ballast and compromised track stability. Today, we will explore how advanced monitoring techniques and innovative solutions can help us better understand, predict, and mitigate risks, and ensure a safer and more reliable railway operation for the future. Thank you for joining us. Railway infrastructure owners are prioritizing resilience with a strong focus on preventive and operational actions. Recognizing that critical risk zones will persist, the key to maintain high safety standards lies in the de-risking of these areas. So, it is important to understand the behavior of landslides to make the right strategy of safety, but also in terms of costs. Landsliding failures are typically slow and localized, and often triggered by rainfall or seismic events. Continuous monitoring helps detect subtle changes before they evolve into critical failures. The beginning is to use remote sensing and survey data like INSAR and LIDAR to enable efficient network-wide screening and identifying these zones with abnormal movement and moisture conditions. From the screening results, critical sections can be equipped with real-time monitoring equipment like sensors, inclinometers, piezometers, etc., to track the performance and support the data-driven maintenance. Early warning and response, integrating data into automatic alert systems and response protocols, enables proactive actions. Using existing and proven technology, monitoring becomes a practical risk management tool, protecting the infrastructure and communities. Effective embankment management relies on a coordinated action across disciplines, departments, and also technologies. Each element, from early screening to long-term reinforcement, contributes to a resilient, data-informed system. When combined, these building blocks form a comprehensive approach to predict, prevent, and respond to landslide and stability risk. We have here the screening, enhanced, and monitoring inspection, which identify and observe the risk zones using sensors, drones, and inspections. The proactive maintenance and reinforcement is to stabilize and drain before failure, prevent rather than repair. Weather and risk forecasting. This is about use the meteorological data and models to anticipate instability. Operational adjustment. Adapt the train speed and inspections when the conditions are not to drive at the normal speed. Data-driven decision-making. Integrate real-time and historical data into models and to guide, prioritize. Safety and continuously planning. Well, it's about having a defined protocol, drills, and rapid response measures. Collaboration and knowledge sharing. This is about to engage experts, agencies, and peer-aligned strategies. So you don't have the only strategy yourself, but also along with your peers. Last but not least, invest in technology. Use AI tools that we know and also will be developed in the future. Using smart sensors and also new and resilient materials for the future. And by that, I will hand over the word to our expert from Geo, René.
Thank you, Niels. Hello, I'm René, and I'm from Geo, and we are pleased to be invited to this webinar, and we'll tell you a little bit about our sides of slope embankment monitoring. Our focus here is the railway in Denmark, because that's what we have worked the most with. But many of these issues we'll discuss are relevant to most countries, I think. In Denmark, we have about 3,600 kilometers of railway, so it's really a lot of kilometers to monitor, and a lot of it is placed outside in areas where we don't come, but we just go past with the train. In many years, we have in many areas we have old embankments with steep slopes, and at the same time there are many sections where we have railway founded on soft soils. And then we see in general we have increased risk of failure because of rising groundwater level. Then we have, it's not an increased risk, but a risk in general that we have deformations of soft soil. And then, as Niels told us, also extreme weather conditions, which is an increased problem and really difficult to design and prevent failures. So we have chosen to divide this presentation into two cases, where the first being sudden failures. The image shows an incident near Quebec in Denmark, when entire railway embankment was washed away. It is a complex case that we have discussed at length in terms of why it happens. The short version of this case is that it was caused by extreme cloudburst and a buildup of water on the one side of the embankment and washed the embankment away. These extreme events can be difficult to prevent, as we cannot design embankments to withstand such conditions. In this case, fortunately, no accident occurred and train traffic was stopped in time, but it could easily have turned into a very serious accident. However, it is possible to prevent an accident by measuring the water level on the side of the embankment, allowing train traffic to be stopped if the water level becomes too high. And I know that this has already been implemented, and in this way, the Danish Banedanmark can help prevent these accidents. But we see it very difficult to prevent a failure of the construction, as we have in this case, because it's really difficult to design, or it will be too costful to design to prevent for these extreme conditions. So the second case we look into is where we have a predicted failure, as we will have in many cases, we believe, where we see some initial deformations in the embankment slope trying to be. If you look at the figure to the right, we see that it's possible to maybe observe deformations in the embankment, and that will happen before we have a total failure of the embankment. So we believe that we can monitor these cases better to prevent failures. So we have taken a known case from at least the Danish railway network. It's a case near Funder in Denmark. This is a very well-known area for Banedanmark, and since I know there are several Banedanmark staff on this webinar, I hope I'll not say anything incorrect. But this area has a slope down to the railway, which then is kind of on a plateau, and after we have a large slope down from the embankment. It's kind of shown on the bottom figure, but we have an embankment of approximately 10 to 12 meters. As it can be seen on the first image, a remediation has been carried out in this area actually because we have some deformations in that area. So it has been repaired, and we have removed soft soil and prevented a failure in that area. The area has been known for a long time, as I said, and the movement of the slope has been monitoring by using small wooden stakes. So you have wooden stakes driven into the slope, which it's then possible to go out there and measure to see if something has happened over the year or every half year when you go out there and measure it. So this is one of many techniques to measure deformations in slopes. Yeah, and this is maybe a better figure to show there. So we see we have a slope down to the railway, and then a plateau, and then we have a large slope again. And what the problem was there was also leading water away. So we have water coming from the top, and then it has not been able to get it down to the bottom of the slope, but it was bleeding, you can say, outside of the embankment, and then you have starting deformations and to build up a failure of the slope. Yeah. Yeah, as I said, there's multiple techniques to monitoring this embankment slope, and I believe an important point here is that one method does not exclude the others, as each has different strengths and also weaknesses. We therefore believe that all methods should be considered in a monitoring program, but it is also important to determine where each one provides the most value. Yeah. So what we have been looking more into is INSAR data as a tool. So INSAR is a radar-based measurement technique that makes it possible to detect movements. So if we again look at the case in Funder we just presented, we have tried to extract data from this area, and as you see on the upper figure graph, it's clear that we have deformations in that area over the years, just to show that this is a tool that can be used to see deformations in area. We would like to further develop this tool, and here we need to take a closer. Oh, if you can go back. So take a closer look at the grid we use the data from. So it needs to be more specific, designed for railway embankments, because we have to have a lot of points near each other on a line instead of kind of a grid, we believe. So in general, we have a lot of data from this this tool, which is a good thing, but it is also very important that the data is used correctly and does not create kind of a false sense of security, since it should be applied proactively to identify potential problem or risk areas, and not as in the Funder case where we only confirm movements in the embankment after the fact. So we see potential in using this as a screening tool, since it's not possible to physically monitoring every kilometer of railway, even just inside Denmark. With this tool, we see a potential for observing every single kilometer of railway and use it to find these risk areas where we see starting failures, or at least starting deformations. And in these risk areas, it is then possible that we can go out there and install sensors, or at least do a more focused analysis of the embankment. Yeah. So another aspect of this INSAR tool is that we also have the possibilities to incorporate additional information into the model. Here on the first figure, we see a cross section with geological data. So it's possible to find areas with, for example, soft soils, as illustrated here, where we have an increased risk of settlement. And with this tool, it's possible to link this with INSAR data, kind of illustrated in the bottom figures, where we couple the geological parts with INSAR data and kind of having a risk mapping of areas where we see a larger potential of risk. And actually, it's possible to couple with further things as sensors out there measuring groundwater deformations, and also weather conditions, because we have a lot of things that actually influence the settlements out there. Yeah.
Thank you very much, René, for this comprehensive insight of two different cases, and also how you use one of the screening techniques that are already existing, but also you will take to another level by using the geotechnical information and add this with the more, I would say, the dynamic screening process. So this is very exciting and something we also believe will be even more developed in the future. So thank you for your input. I will now continue, and I'm happy that you mentioned this screening tool here, because we also, of course, use this as input to some of the business that we're doing. We also get information, and the infrastructure owner get information from the more traditional way, the periodic measurement trains. Also from point clouds, which are also highly implemented throughout the infrastructure. And last but not least, also drones that are been inspecting the railway and the surroundings around the embankment and the forest and the drainage and so on. So this is typically technologies that are being used to provide information from the overall screening process. And now we will move into now we have the screening. We have localized the different areas where there could be some critical risk zones. And now it's time to make the monitoring strategy. So as René also told before, groundwater level is important to monitor, because this has a great impact. Of course, also the water next to the track, the exact embankment, the movement of the embankment, the embankment stability, the moisture, which also change due to the water level next to the tracks, and also the subballast moisture, which also indicates that there could be some movements. And finally, also the drainage system, which is of course also important, as René mentioned. One of the issues in the case he mentioned was that the water could not get away from the embankment, which led to the embankment to slide. And so this is different approaches for more detailed real-time monitoring. And of course, we cannot do everything all the time, because it's also a matter of costs. However, this is the monitoring strategy. Last but not least, you can also combine this with information from the weather, and this is also quite crucial, because then you in advance can make your precautions. When you know that there will be a heavy rain, you might slow down the speed of the train, or maybe even stop them if it's very critical. I have now one example from an embankment monitoring project. So as you can see here, this is the track. You have an embankment on the right-hand side. You have an embankment slope on the left-hand side. There are sensors on poles, both in 2 rows. And the reason for the 2 rows is to monitor, of course, have a more comprehensive view of the embankment. If you have a sketch here on the right-hand side, the poles can be put on the top. In this case, the strategy was only to put on the left-hand side. The distance between the poles are in this case 25 meters. It is placed in 2 rows as said. So in practical, there will be 12 and 12.5 meters in between the poles. The poles are then hammered in the soil, and when the soil are moving, then you will be able to monitor this in real time and get the notification. And for this case here, this is an example. So in this case, you have data from actually New Year this year, and here we have 8 sensors that are in an embankment, and we see that that before the New Year everything was stable, and after New Year it suddenly starts changing, which indicate that something happened on the embankment. This is where the protocol of, well, what do we then do when we see something like this? So once we have the screening, now we have the monitoring, and then we have the notification. So this is the chain of the data and the decision taking. And this leads me into the intelligent monitoring logic. So in the next couple of slides, I will make a more detailed view of monitoring samples from the strategy and to the alert and notification. So what should we do, and what is the strategy for the monitoring? What kind of alerts do we need? Once there is an alert and it's triggered, who should be notified? And what information does the notification contain? So in this case, the embankment has shown some movement. So that has led into a temporary train speed reduction. The objective here in this case is to monitor settlement behavior and correlate with data from the measurement train. At present, the speed restriction remains in place, even though that there are now a monitoring system equipped. But the goal is to verify that the stability and eventually can remove this limitation. In collaboration with the infrastructure owner, both sides of the embankment are being monitored. So you can see here on the right-hand picture that here the sensors are placed on both sides of the track. They are mounted on poles and insert approximately 1 meter in the ground and spaced around the 25-meter intervals. So what kind of alert do we need? Well, many use intelligent sensors that are equipped with intelligent firmware and that can respond locally and transmit data immediately when changes occur. However, the monitoring software remains essential. It provides the capability of analyze trends, detect anomalies, and also issue the alerts. And here we see 3 types of alert functions in actions. We have the threshold alert, we have the sudden change alert, and we have the forecast lens alert. The threshold alert notifies when a present limit has been set. The sudden change alert is activated when a sensor value sudden changes its value. And last, the forecast alert is based on what in our system we call the forecast lens function. The forecast lens function is an analytic model which is trained on historical data. The threshold here is set using advanced algorithms. The poles, in this case, which are in the soil, moves daily both in X and Y direction. So this is just the normal behavior. And then the algorithms learns this natural dynamic behavior and sets the individually limits for each sensor, so you do not get any false alarms. This combined with the forecast lens function concludes that both the sudden change and the forecast lens alerts are recommended for the embankment monitoring using pole sensors. And if we use this information for the last real data we saw before, you can see here that we we have the forecast lens and the sudden change. So this is the sudden change alert that actually notifies based on this value here and the value here. So this was actually what actually triggered the alert function. So when you have the alert, who will then get the information? Well, it is possible by the software to get a notification schedule. So you have different persons in different time intervals to receive the data. And when you get the information on your mobile phone, is also important to get the right information. So having this, the sensors that are being installed in real and monitored in real time, having this information about who to notify and when, then it's also important to know where to send out, and also to make the decision where to send out the people, and also which kind of train you need to inform, maybe to slow down the speed or even maybe stop the train. So the alert protocol is very critical to ensuring that the right people are notified immediately and provide with accurate, actionable information, and to enable the prompt decisions. So by saying this, I will end my presentation, and I will hand over the word to Kristen, and he will have the...
Yes, thank you, Niels. Thank you very much. Well, I just want, before we go into the Q&A session here at the end, I just would like to point out that we will do another webinar. This one, the next one, will be about monitoring and control directional drillings. And we will do this on Wednesday, December 10th, same time, 9 to 9:45 a.m. And you're all welcome to participate. Thank you very much.
And Christina, you have the word for if there's been any questions during.
Yeah, well, so
session.
there are no questions.
There's no questions.
Fantastic.
I think that you must have been well spoken in the information given so far.
Maybe, but if you have any questions, you of course always free to reach out to us, and we will be happy to engage, and also Renee, we will also provide this webinar, and we have recorded it, so we will also send it, make it public, and but I will thank you very much for joining the session today together with us, and I wish you a nice day then.
Thank you all.
Yeah.
Bye-bye.
Thank you.
Bye-bye.
Bye.